Okay, so tonight we're going to do a discussion on what is reality.
Oh,
Got a minute?
far out. Okay.
And we'll start with this.
That was from Father Guido Sarducci on Saturday Night Live, by the way, just to give full
What's that?
disclosure and footnotes. That was Father Guido Sarducci would say on Saturday Night Live. They'd
Oh,
ask a question like this, and he would say, "Got a minute?"
oh, I see. All right. I got a minute or two or three or four.
Right. So it's actually, there's quite a lot of stuff here, but it's the presentation itself is a very short one. So we're going to start just with the assertion that really there's multiple views of reality, or to put it differently, we're not sure that there's a single reality. So we'll see where this leads us.
Putting it mild.
Yeah. So the first one is we start with something that I hope is very constrained. Everybody usually in elementary school or middle school comes across this experiment that Michael Faraday did in the 1820s. He took a bar magnet and he placed a piece of white paper over it, and he sprinkled iron filings onto the white paper. And in doing that, what happened was the iron filings aligned and formed lines of iron filings that went from the North Pole of the magnet and circled all the way around to the South Pole of the magnet. So here's a picture of this actually from, I don't know if you can see this, hold on. There's no sound, so I don't need to worry about that.
Okay.
But here's a picture of what Faraday did, so you can see the filings kind of run around and they're circling around. They're going to come back here.
I don't see the picture.
You don't see right. We got to do the share screen doesn't work without the picture. I see. Okay. Well, I learned something. Okay, so let's see how I fix this. What I'm going to do is I'm going to copy this. Let me close it. Let me get out of share screen. Let me go back to the browser. Now I'll go back into Zoom, into share screen.
There it is.
And there it is. Now, do you see this?
Not yet. Oh, okay. Okay, now I do.
Yellow and turquoise
Yeah.
with little bugs lining up.
So you see the iron filings there.
Yeah.
And he's got two different magnets apparently, but the iron filings line up and they circle around going to the other. There's one magnet here going around to this one, and there's one here going away, and it's going to come around. You can see it circling around back down here. So this is his actual original 1820s experiment. The date on this was 1851 because he did it repeatedly over the years. Okay. But anyway, that's what everybody remembers. Okay. So now what we're going to do is something else. Hold on. The key thing was there's the magnets and there's iron filings. Okay.
Right.
And the problem with that is that the iron filings by themselves end up distorting things. Okay. Hold on.
An early collaboration of ours.
Okay,
My sister's old TV.
okay, so now we're going to go back to Zoom. And we're going to show you a different experiment.
Doesn't seem to be there.
Wait, hold on, I lost it.
I'm sure glad you guys are doing all that and I don't have to.
Well, thank you for being our patient guinea pig.
Okay,
There
here it
we go.
is.
I wonder if it's going to show.
Hold on.
That was it. It was that gray looking screen.
You sure?
Yeah,
This one here?
yeah.
Yeah, there it is. You're right. Now we're going to do share sound. Now, this is a movie. This is a movie that I put together on my phone. And so what you've got here is a bar magnet, okay? But there's no iron filings now. Okay, this is the key thing. Here's the North Pole is here on this side. It's a cylinder, okay? The North Pole is on this side, South Pole is on this side. So you can see the filings kind of going around globally. Okay, move it. Okay.
It's super strong as a magnet.
Yeah, it's a very, very strong
We
magnet.
can't, just put it any place in the
Yeah,
house.
yeah. So what we've done is we've got it sitting on a old cathode ray tube television screen. Okay. Now the screen itself doesn't have any iron filings in it. It just has phosphors. You know, there's some that get stimulated by red light, some by green, some by blue. So the phosphors we turn the TV on, but the TV is not plugged into any TV antenna. There's no signal going in the TV. So the only thing that's on is the screen, okay? But the screen is sensitive to electromagnetic fields.
Oh,
Because of these phosphors, because that's what they're designed to do, is to interact. So if we take a look at this thing, this is a little movie put together. Okay, move it a little bit. Rotate it. Yeah, we'll just rotate it. A little more. Yeah. Okay, stop there. That's good. Now, the problem with this is
Did you see a clover leaf like pattern?
Yeah, you're going to look for a clover leaf. So take a look at this and watch. And you see there's the clover leaf. They see 1, 2, 3, 4. See, there's multiple things going in and out there.
Like striations in the static.
Yeah. So what's going on is the actual magnetic field comes out of the North Pole and then doesn't go to the South Pole. It goes to the middle of the magnet, goes into the magnet in the middle. And then where it goes in, coming out of there is another magnetic field that curves around to the South Pole. So instead of having what Faraday saw, which was the North Pole and the South Pole, and the magnetic field lines go from the North Pole to the South Pole, they in fact go from the North Pole to the middle of the magnet, and from the middle of the magnet to the South Pole. Okay, so this is like one of the simplest things you can come up with. Let's see if we can run this again. There, that's good. Hold on, we'll run it again.
I want the audience to know that's my hand rotating. the magnet.
Rotated, yeah, we just rotated.
Taking the picture and Marjorie's rotating the magnet.
On the screen. Okay.
Yeah, it's right on the screen.
Can you
There,
see?
see, there you go. See the clover leaf that was there? That was showing it going in and out.
Okay, move it a little bit.
When I try and stop it, see, this is what happens. I stop it, everything gets scrambled. See, I stop it, it gets scrambled. Just stop it and get scrambled.
Rotated.
See? But this
Do you
is
see this clover pattern?
there you go. You can see it's not a simple thing that goes moves around. You can see there's 4 things there, 4 ears. Okay.
Just 2.
Yeah.
Like this.
Yeah.
Okay, move it a little bit.
So this is
Yeah,
just a hint that, again, when you start to look at things,
A little more, yeah.
That looks
just
like it's got 6 or 8.
yeah. No, but there's 4
good.
right there. There were 4 there.
That's 4.
Okay. So anyway, so this is an example just to show, again, what is
Between
reality?
1990 and 2003.
Get rid of this. Okay. So now we'll go back and do our favorite. Hold on a second. Our thing, which we showed before, which is what you saw with Ron, and that's this double slit experiment.
Oh, right.
And again, we're just trying to get at what is reality.
The granddaddy of all quantum weirdness, the infamous double slit experiment.
Hold it.
To understand this
I
experiment,
forgot to turn on the sound. Hold
I
it.
can, oh,
Could you hear the sound
yeah,
from this?
to understand this
Can you hear that?
experiment, we
Yeah.
first need to see
Okay.
how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the 2 tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through 2 slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through 2 slits, we should get, like the marbles, 2 bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So They decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay.
Kind of cute.
Oh, wait, hold on. Let me shut this thing off. Hold on. Hold on. We got a whole bunch of, hold on, I'll get rid of this. Okay. So now where are we? We're here. Okay, so go back to our, oops, wait, I'm going to do share screen. Hold on. I got two of these. There we go. Okay, so we start to wonder what is real, okay? So what Ron observed was that the electron was coated with these blocks of information that were constantly scanning the world around it. And so in this single slit versus double slit experiment, when the electron, by scanning before it went anywhere, saw that there were two slits instead of one slit, it immediately turned into a wave. There was no time. As soon as this happened, as soon as there were two slits, the electron as a particle disappeared and the electron as a wave was there. If you had an observer, then the electron would scan and see there are two slits, but there's also an observer. And the rule for that is you behave like an electron, not a wave. So this is what he came up with that reconciled what's really going on here. Of course, it raises the issue of what are these blocks of information and how are they scanning all this and what's the physics of that? But we're not going to deal with that here. That's what he observed. Okay.
What I want to know is how do they know to interpret an observer?
Well, they have a set of rules and a set of algorithms, and they go to the book and they look up and it says if there's two slits and no observer, you do this. You look like a wave. There's two slits and an observer.
How do they know a broom handle from an observer?
Well, I don't make up the rules. I'm just telling you that that's what they do.
Well, I think some experiments should have been done to explore this.
Well,
What if it's something with no perception that's just sitting there? Does that affect it?
Well, they didn't realize what Ron saw was that the electron was scanning all by itself the world around it.
Right,
You know, they have no mechanism for detecting those scans.
right.
If they did, then they would start to come up with experiments. But right now, there are no such.
Well, it's still an anomaly to them. I mean, what-
Yeah. That's what they said. So it's just one of these things. This experiment was first done in the 1920s, and here we are 100 years later, and people are scratching their head wondering what's going on. So this led to a lot of work, though, in physics, with what's going on with an observer. I just have a reference here to this guy Stephen Wolfram. Let me just click on it so you'll see. So he's got a video here.
Grammarly is basically like an AI writing partner.
Sorry.
I don't see the video.
No, we're not going to go into it.
Oh, okay.
He's got a video on this, but really what he's saying is that let me go back to the, what do we do here? We're still screen sharing. Okay, here we go. But what he was saying is that we have a theory for computing due to Turing, where we have a model that describes what any computer does in an abstract way. And he said we need a similar theory for how the observer behaves. But he's at an early stage of trying to formulate what the algorithms would be for this observer. And he basically has been derailed doing other stuff, but he is cognizant that there's a problem that he has that he can't explain, which is how does the observer influence what's really being observed? What is reality? Okay.
Well, but as I keep saying, how is it known by what or whom that the observer is an observer?
Right. Yeah.
What if you just
what makes you an observer? Why?
Right.
As Marjorie said, what if you're a broom handle sitting in the corner of the room? Does that mean you're an observer? No.
Well, I don't know if we've ruled that out. It's to me, it's got to be tested.
It just shows how little we can say about basic things like this. So now let's go to the main guy here, which is, hold on a second, I got it here. Okay.
This is Bart's hero, Roger Penrose.
Yeah, Roger Penrose is this Brit, and he received the Nobel Prize in physics in 2020 for work that he did. Oops, wait a moment, hold on. I didn't get the, hold on, let me get out of this. I wanted to get the sound to work on this.
Box. It knows it's being observed, so it's not going to let you do it.
Here it is. We do have sound sharing here. Okay, it checked. Okay, so we're cooking with gas. So he has a series of talks, and I referenced them in the PowerPoint. But this one that we're going to look at is just half an hour, and it will cover. It's a summary of what's in the other three that collectively add up to more than an hour. Okay, so we'll just focus on this one, and I will stop it from time to time to try and pick up on things he's saying, to try and clarify things that for him are totally obvious, but if you don't have his background, you don't know what he's talking about. So we'll see how I do. So here we go. We're gonna let it rip. Okay, do you hear sound, Bruce?
Yeah.
You hear sound? Okay.
Roger Penrose, mathematician, physicist, philosopher, was awarded the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. I had the pleasure of interviewing Roger in depth twice, in Oxford in 2007 and in Tucson in 2014.
Now for something.
We covered many of Closer to Truth's fundamental questions. What things exist? Is mathematics invented or discovered? How did the universe begin? What is consciousness? While Closer to Truth has featured Roger on specific topics and in TV episodes, we now integrate his work and present a comprehensive sense of his remarkable thinking. But to do so, I wanted to speak with Roger again, currently, hear his retrospective, check his views. We discussed three favorites: what things exist, what is mathematics and why does it work, what's fundamental in the cosmos. I'm Robert Lawrence Kuhn, speaking with Roger Penrose to get closer to truth.
Emily wanted to create something special for her husband, something delightful.
In mid-2022, planning the Closer to Truth retrospective on Roger Penrose, I had an extensive discussion with him in three parts. Due to pandemic constraints, we spoke online. I start with a core Closer to Truth theme. What things exist? Let's start with your grand metaphysical framework, your three worlds, three mysteries, the physical world, the mental world, the platonic or mathematical world, each connected to the other two in your famous diagram of an equilateral triangle.
The picture, of course, was influenced by that particular impossible triangle, which was deliberate in a way.
Yeah, so here you see a picture of, it's not an equilateral triangle. This is from Escher. So there's no way for you to actually build this thing, because you have this side comes down here, here's its top, and it goes over here. Okay, but then it comes up here, but then it goes down here. Okay, so like this is impossible. Okay,
Right. Okay.
but that's why he chose it. It has three nodes to it, and that's what he's going to talk about, the three entities.
Because in the picture you see a mathematical world at the top, which I regard as having its own existence independently of us, and a very small part of that has to do with the physical world. We know when we get the mathematics of our physics right, it's very, very precise. However, it's only a very small part of the mathematical world which governs the operation of the.
Yeah, so let me just expound on it. He's going to bring this up later, but there's lots and lots of people that are now mathematicians. There's more mathematicians today that are doing mathematics than have ever been in the history of the world. And they're continue to crank out all kinds of things. And there's journals that are just filled up with papers on mathematics. And if you go look at these papers, you'll see that they're all filled up with all kinds of mathematics, which is interesting to other mathematicians. But most of it bears no resemblance or any utility to anything that you or I would ever deal with. Okay, it's just abstract thought. It's very nice. But it's always true, assuming that the proofs are done correctly. That isn't in doubt. But it lives in its own space, and a very small fraction of that might have to do with our physical world. So the fraction that people point to is they point to gravitation and electromagnetism. And in gravitation, probably due to Newton, you ended up with a fit of 1 part in 10 million, okay? There was discrepancies that occurred when you looked at things in the 7th and 8th decimal places that Newton couldn't explain. But, that's not too bad for first cut to be good to 7 significant figures. Electromagnetism was even greater. That's good to at least 12 significant figures right now is what we have. And when Einstein got involved in looking at gravitation with general relativity, he was able to tweak it to take it out to 14 orders of magnitude before it started to have problems. So when you say that there's a match, that's not too bad. Be able to take some theory and put some numbers in and get some numbers out, and voila, and it matches what's really going on in the physical world. But it's all totally mental. In fact, Einstein did all of his work totally abstractly. He was just thinking about gravity. He didn't run any experiments. He knew there were things that couldn't be explained, and he said, well, let me come up with a theory that might explain them. But it was entirely mental. Okay, there wasn't anything done. So that's why he's trying to point out mathematics is this big area, and a very small piece of it has something to do with our physical world.
Physical world. So I represent this with this sort of beam coming down, and physical world being encompassed in this very tiny part of the mathematical world. When in the physical world, we have these conscious beings, and these conscious beings are a very small part of the physical world. And I regard this consciousness as having a different kind of existence, but it springs from that very tiny part of the physical world. But that in the world of conscious experience, we also have understanding of mathematics. That again is a very tiny part of mentality. And so that, in a sense, encompasses, or at least has the potential to encompass, the top world, which is the mathematical world. And I sort of draw.
So what he was saying is, the physical world, a piece of it is human beings, for example, but then there's other things like rocks. Most of the earth appears to be inert matter. There's nothing conscious about it that people are aware of at this point. But the people that are alive have some mental activity, and that leads to that mental realm. And a very small piece of that mental realm, people are mathematicians, and that leads to the creation of mathematics. So you end up with this crazy situation where a little piece of math deals with the physical world, a little piece of the physical world deals with the mental world, and a little piece of the mental world deals with the mathematical world. But they encompass all of them. So that's what he's trying to get across here, is this three-part view of reality.
Well, this is a kind of paradox, because it's a small part of each world which seems to encompass the totality of the next one. And it's deliberately drawn as paradoxical just to emphasize the strangeness of the whole thing, I think.
It was good to see Roger again, immersed in his special way of framing reality. I recall our earlier conversation in 2007 in Oxford, developing the same theme, What Things Exist. 3 worlds, 3 mysteries.
Mathematics seems to have its own kind of existence. It's very important in understanding the physical world, that our way of describing the physical world, certainly at its most precise, has to do with mathematics, and there's no getting away from that. And that mathematics has to have been there since the beginning of time. It has an eternal existence, timelessness, really. It doesn't have any location in space. It doesn't have any location in time. Some people would take it not to have any location or not any existence at all, but it's hard to talk about science, really, without giving mathematics some kind of reality, because that's how you describe your theories in terms of mathematical structures. It has this also this relation to mentality, because we certainly have access to mathematical truths. But I think it's useful to think of the world as not being a creation of our minds, because if we do, then how could it have been there before we were around? Somehow, if the world is obeying mathematical laws with extraordinary precision since the beginning of time, well, there were no human beings and no conscious beings of any kind around then. So how can mathematics have been the creation of minds and still have been there controlling the universe? So I think it's very valuable to think of this Platonic mathematical world as having its own existence. So let's allow that and say that there are three different kinds of existence: the normal physical existence, the mental existence, which seems to have, in some sense, even greater reality. It's what we directly are aware of, what we directly perceive. And the mathematical world, which seems to be out there, in some sense, conjuring itself into existence. And then there's the relationship between these three worlds, which I regard as, all three of them, as somewhat mysterious. Mystery number one is, how is it that the physical world does, in fact, accord mathematics to such a fantastic degree of precision? So that's mystery number one. Mystery number two is, how is it that when you have physical structures of the right kind, and here I'm referring very specifically to living, human, wakeful, healthy brains, somehow it's evoked when the structures have the right character, whatever that is. Mentality seems to have this deep relation to certain kinds of physical structures. Mystery number three has to do with our access to the world of mathematics. And why it's a mystery is perhaps not so clear, but it's something that you certainly can't describe in terms of purely computational activity. There's something outside that in our appreciation of mathematics. Even just knowing what the natural numbers, 0, 1, 2, 3, 4, I can say that, you see, and you can explain to a child, and they know what numbers are, but yet you can't characterize simply by axiomatic procedures what the natural numbers are.
Yeah, let me just pick up on what he just said. So you have the natural numbers 0, 1, 2, 3, 4, etc. And those numbers, people have struggled to come up with a set of axioms or something that would allow those numbers to exist. And finally, this German mathematician in the 1850s, Kronecker, said, okay, I give up. God created the integers and man created all the rest of it, okay? So for example, when you have the integers, you can define what he called rational numbers, which are ratios of integers. So I could have 1 over 2, 1 over 3, 1 over 4, 2 over 5, 7 over 29, and so forth. So these are all rational numbers, and they fit in somewhere in between the numbers 0, 1, 2, 3, etc. You also have negative numbers going -1, -2, -3, okay, that come out of this. You have a whole bunch of other things that result from this. One of the things that mathematicians get intrigued with are prime numbers that are themselves either they're the product of themselves, and no other product of numbers could give you that number. So those appear to be interesting numbers. They're unique. So the prime numbers go 1, 2, 3, 4 is already 2 times 2, so that isn't prime. 5, 6 is 2 times 3, so that isn't prime. 7, 8 is 2 times 2 times 2, so that's not prime. 9 is 3 times 3, so that's not prime. 10 is 2 times 5, so that's not prime. 11 is prime, and so forth. So they're scattered among the numbers, and they have their own, if you will, life to them in terms of how people study them. So that's the world of mathematics that appears to be underlying everything, except that we don't really know why.
Say that. Yet how do you know what they are if you can't describe in a finite set of rules what these numbers are? There's another feature about this, which is that in each case, it's only a small part of one world which encompasses, ever seemingly, the entirety of the next world. So, okay, it's only a little bit of mathematics, okay, a very subtle and beautiful and powerful part of mathematics, but there's that whole world of mathematics. If you look at any mathematical journal, pure mathematical journal, it's full of things have absolutely no relevance to physical activity. So it's a small part of the mathematical world which seems to encompass the behavior of the physical world. And it's a very small part of the physical world which seems to evoke mentality. Okay, there are far more rocks and things, dead planets around than there are conscious brains around. And it's only a small part of our mental activities which relate to mathematics.
Now, the typical scientific response to that would say, okay, the mental world is just an expression of the physical brain, and mathematics is very nice, but it's something that human beings have invented to sort of describe the physical world. So there really is only one world. The other two are kind of derivative or imaginary.
Well, you see, you could take that view, or to a mathematician, you might take that the mathematical world somehow is the one, because somehow it has to be there. You see, it sort of creates itself out of nothing. You see, and it has to be there. And then the physical reality, you might think, has its source in there. Or you might say, well, no, it's mentality. That's where all our knowledge comes. That's everything. Ultimately, is to do with our consciousness. And everything else is then explained in terms of it. So it isn't clear.
Each one of the worlds can feel its own predominance over the others.
I think that's right, yes. I'm trying to make it look a little more kind of symmetrical and even-handed. And to a mathematician, the mathematical world has a kind of reality out there. It's if you like, the reality of the mathematical world, the Platonic world, is an expression of the objectivity of mathematics. There is outside of us something there which is beyond any individual mathematician, and beyond the totality of all mathematicians.
From what things exist, the natural progression in Roger's unique thinking is to focus on mathematics, its essence and effectiveness. What is math, and why does it work?
I'm not going to take a view really to say that anything is more real than another. I mean, I've been slightly talked into saying that the mathematical world is more fundamental, which in a certain sense I do think, because it has to be there even if the other two didn't exist in that sense.
Here's Roger on mathematics in Oxford, 2007, 15 years prior. How accurately does math describe the physical world?
Well, it is extraordinarily precise. I think people often find it puzzling that something abstract like mathematics could really describe reality as we understand it. I mean, reality, you think of something like a chair or something, something made of solid stuff. And then you say, well, what's our best scientific understanding of what that is? Well, you say it's made of fibers and cells and so on. And these are made of molecules, and those molecules are made of atoms. Those atoms are made out of nuclei and electrons going around. And then you say, well, what's a nucleus? And then you say, well, it's protons and neutrons, and they're held together by things called gluons, and their neutrons and protons are made of things called quarks, and so on. And then you say, well, what is an electron and what's a quark? And at that stage, the best you can do is to describe some mathematical structure. You say they're things that satisfy the Dirac equation or something like that, which you can't understand what that means without mathematics.
Now, mathematics can also describe things in the ordinary physical world, gravitational attraction, electromagnetic attraction, and with the same kind of descriptive accuracy?
Well, there's another, even more in a certain sense. Newton's theory already had a precision of something like 1 part in 10 to the 7, so that's 10 million.
Wow.
And then Einstein comes along and produces a theory which is now known to have a precision something like 10 to the power 14.
So what does that now begin to tell us about what mathematics really is?
Yes, well, in a sense, this is telling us that our picture of physical reality depends on something, in a sense, which is more precise, at least in our understanding of it, than how we think about the world. It has its own life, in a sense, and certainly mathematicians view it this way. It's something out there which seems to have a reality independent of the reality, the ordinary kind of reality, like things like chairs and so on, which are what we normally think of as real. But okay, the mathematical reality is something different. It's sometimes referred to as a Platonic world, a Platonic reality.
What would that mean, a Platonic reality?
Well, I tend to think of there being different ways of looking at reality. There's the reality of our mental experience, which interrelates with the reality, the physical reality, but so then does the mathematical reality of this Platonic world, which gives reality to these notions. So if you like, mathematical facts, like there is no largest prime number, it's something independent of ourselves. It's always been true. And in a sense, that had to be so, because if the physical world depended so precisely on these mathematical laws, I couldn't have known what to do in a certain sense if the mathematics hadn't already been there.
Well, that's the argument. Whether mathematics is invented by us, by human beings trying to impose our way of thinking on the physical world, or whether it is discovered because it's already out there and we're finding it because it's already there. Those are the two polar views.
Sometimes people do argue. They say, well, you know, it's just our way of organizing the what we see about us. But I really don't think that's good enough. Einstein produced his theory mostly out of his head, without appealing to things that were known to Galileo and so on. But apart from that, it was not much more empirical evidence. But he produced his theory, which extended far beyond anything that the observations at that time told us about. And they keep on agreeing with the observations. So that theory, which is, if you like, a Platonic absolute thing, I mean, it's a mathematical thing, seems to be inbuilt into the way the world operates. I like to think of mathematics as a bit like geology or archaeology, where you're really exploring something out there in the world, and you're finding beautiful things or things which have been there, in fact, for ages and ages and ages, and you're revealing them for the first time.
Some of which you never dreamed of.
I've never dreamed of some of them. That's absolutely right.
Yeah, so let me just give you an idea of where this is going, okay? You had, someone like Newton in 1680, he published his treatise, Principia, and that explained how planets and moons and stars attracted one another. But it took, hundreds of years for the telescopes to get there to be able to start to see what was really going on. It was a theory that was ahead of its time, okay? We had Maxwell pulling together a lot of experiments that have been done in 1750 on up to 1850, and coming up with a set of equations that described electromagnetism. And it was that really only kicked in 50 to 100 years later with electric power and motors, generators, and lighting systems, and everything that went with it. So these things were really in advance. So if you look at today, what is going to be the thing that carries the day? There's a mathematician named Ramanujan who was no one knows how smart he was. Okay, he was an Indian, and he approached in 1920 G.H. Hardy. He was on the math faculty at Cambridge University, and Ramanujan sent him a bunch of things that he'd put together. And Hardy started looking at this, and he said, I've never seen any sort of functions like this in my life. So he invited Ramanujan to come to England, and he came to England, and they started working together. And Ramanujan kept cranking out one thing after another, which only today, literally in the year 2020, are we coming to grips with what Ramanujan did and where we might in fact use this in different areas of mathematical physics. He was so far ahead of his time. A different example is a guy that I interacted with at Bell Laboratories named Phil Anderson, and he received the Nobel Prize in Physics for work he did in what's called solid state physics, which is the physics of transistors and semiconductors and anything that's solid. That's why it gets its name. But he himself came up with a lot of ideas about superconductivity, and he was credited with the idea for really what became the Higgs boson that Higgs noticed, because Anderson noticed there was a duality between the theories in high energy physics and the theories in solid state physics. and a mathematical duality, and he exploited this again and again, and that led him to the creation of this Higgs boson, but also what we today call string theory in physics. And again, he was way ahead of his time.
That's the height of fashion.
Yeah, we're just trying to come to grips with what in the world he came up with. These ideas are just coming into play now, and so that's Penrose is this sort of guy that he works on things that are 50 years out. Okay, that he senses I'm in the right area, and let me just go at it, and we'll see what happens. So this is, let's dig into this some more, and you'll see.
From the deep essence of mathematics, especially math's role in describing, perhaps in constructing physical reality, it is again a natural progression to what's fundamental in the cosmos.
I was in my final year at University College London, where I did my undergraduate work, and in mathematics. And I heard a series of lectures by Fred Hoyle, where he described his version of what was referred to as the steady state model. At that time, there was a great puzzle because the universe appeared to be younger than some of its contents. There were these collections of stars called globular clusters, and they were calculated to have existed for longer than the universe seemed to have existed for, which was a paradox. There was actually a mistake because of a confusion between two different kinds of variable stars, but that wasn't known at the time, and the steady state model was evolved to encompass it. You say, well, the universe doesn't have its origin at the Big Bang, but it went on continuously. And it was the problem I had with this picture that Fred Hoyle described, right? The galaxies. He said they would go further and further away, getting faster and faster and faster. And when they exceeded the speed of light, they would disappear from view. And I drew little diagrams and light cones and things, and I didn't see how this could happen. I thought they would fade away and not disappear. And so I asked my brother, what's wrong with that? And why I don't think I quite agree with Fred Hoyle. And he said, well, I don't know anything about cosmology, but sitting on the table over there is my friend Dennis Sharma, and he will tell you the answer. So I described my thing to Dennis, and he said he hadn't seen this way of reasoning before. And then I went to Cambridge as a graduate student in pure mathematics, and Dennis sort of made a special beeline for me, and he decided he wanted to teach me cosmology.
Roger famously takes intense interest in the initial conditions of the universe and how incredibly extraordinary it had to be. We discussed it in Tucson in 2014.
Roger, you have thought deeply about the origins of the universe and have come up with a very mathematical description of what the initial conditions of the universe would have to be like.
One of the most fundamental principles of physics is the second law of thermodynamics. And the second law of thermodynamics, roughly speaking, tells us that things get more and more random as time goes on, or if you like, the entropy, which is a sort of measure of randomness, is increasing all the time. Now, okay, that's our experience, but there is an issue when you worry about, where it came from. Now, let's just say, okay, if entropy is increasing in the future, an equivalent way of saying that is that it decreased in the past. So that means you go back and back and back and back, you reach a low state of entropy. What's the place you get to? The Big Bang. Well, one of the most striking pieces of evidence for the Big Bang is this thing, sort of curve that people plot, which is the Planck curve that seems to be very well fitted by the radiation coming from the Big Bang, the microwave background. And that is a puzzle, because what do we see? We see evidence for what's called thermal equilibrium. Thermal equilibrium is maximum entropy. So you go back and back and back in time where you should find the lowest entropy, and you find a maximum entropy. That's just obviously funny logic, you see. Well, it's not illogical for the reason that what we're seeing is simply photons coming from matter, roughly speaking, in equilibrium, so high entropy state. As far as the photons and the matter running around together are concerned, yes, it is a maximum entropy state. That does not take into account gravity. Gravity is very special in the universe as we see it, particularly at the Big Bang, in the sense that it was very uniform. Now, uniform, that's a sort of gravity strange in this way, because when things start to clump, you produce galaxies, stars, and so on. These come about through the clumping of material, and that's raising the entropy. So you get a more clumped state as the entropy goes up. So what you see is a uniform state, and when gravity starts to come into play, it becomes less uniform. But that is all the time raising of entropy. So there's no inconsistency with the second law. It's just it looks funny. It looks more clumpy, whereas if it's just been matter and radiation, it should remain uniform. I mean, there's always been a great puzzle to me, which is why in the Big Bang that gravity was not activated. Everything else seems to have been randomized completely, but gravity was aloof, was kept back. You got this very uniform state, which means low gravity, no gravity. For a long time, I just played with this idea and made a hypothesis. I thought maybe it was some aspect of some peculiar quantum gravity theory, which had to be asymmetrical in time, because it's quite unlike what we get in black holes. In black holes, you get gravity dominating. Gravity is the main feature of the mess you get at the end. It's simply not present. If it were a theory of singularity structure, which was quantum gravity theory, it should be a time-symmetric theory. Gravity and quantum theory are both time-symmetric. Why is it so asymmetrical? So I had to think of maybe crazy quantum gravity theories or so. But my ideas have changed, really, in that it's not really quantum gravity at all. You see, in a sense, it's an argument against quantum gravity, because if quantum gravity ruled at the Big Bang, there should be a contribution from all the other things which might happen. And there simply isn't. Well, that was a driving force behind my CCC, conformal cyclic cosmology scheme, with all the eons, which is that in order to make it work, the way the transformations work to fit the exponential expansion of the previous eon into the Big Bang of ours, you've got to kill off gravity. You can't help it. The degrees of freedom in gravity are not killed off, but they're transformed into ripples in the new material, which also the equations tell us have to be there, which I call the initial form of dark matter. Now, you see, that's another mystery. What is dark matter? Now, people say, well, maybe it's some super partner of some, you see. I say it's not that. It's something which naturally comes along as a partner to gravity, which comes along when you treat gravity in accordance with this conformal scaling idea. And then you find that when you transform from the remote future of the previous eon to the Big Bang of ours, there has to be this new material created. It would be the dominant material in the universe. It would also have to decay gradually over the whole eon, so it's none left by the end of the eon.
To make the initial condition for this universe work, you talk about a very, very high order of magnitude of...
Yeah, I'm gonna come back to this, but let me try and touch on what he's talking about here. So if you take the current thinking, which is that all of the galaxies are flying away from one another, and that space itself is expanding, then you end up with everything just going off into all directions till the end of time. So what he came up with as an idea, and this is something that I think Ron was trying to deal with in his own way through his own capabilities, is what's called a conformal mapping. So let me give you an example of this so you'd understand what he's talking about. We take a sphere, and the sphere has a north and a south pole. So we'll grab the north pole of the sphere, and then we'll run a plane through the equator of the sphere, and the plane will go out forever. Okay. So when I'm here on the north pole of the sphere, I'll take a look at a point out on this plane, could be 20 miles out, and it will I'll take a line from the North Pole. It'll go inside the sphere and then hit the sphere on a certain point, and then go outside the sphere and hit this point way out on this line. Okay. So what he's saying here with this conformal mapping idea, the mapping is what I just described. We're going to map every point on the sphere, going from the North Pole out to some point way out in this plane. The conformal mapping is every point in the plane will correspond to a point on the sphere. So as things get spread out more and more and more, he's envisioning the universe, in fact, getting back together conformally. It simply flips on itself and compactifies. And what we see is the remnant of the earlier universe that was there when we got when everything came back together. Everything got so far apart that it conformally collapsed on itself into what is our current universe. And he views this as something that's cyclical, that you have bounce after bounce after bounce occurring as things get compactified, and then they spread out, and then this conformal mapping kicks in and you come back together. So it's an idea that I'm giving you an example of the conformal mapping taking place in three-dimensional space. But what Ron observed was we have 24 spatial dimensions. So you have to figure out what a sphere in 24 dimensions looks like, and then draw a plane through that sphere and do the conformal mapping for that. But that's left as an exercise for you to go work on in between classes. And so the other thing that he's talking about here, just to go back to Fred Hoyle, was Hoyle said, well, probably what's going on in the steady state is that all of these galaxies are moving away from one another, and space itself is empty, and all of a sudden matter gets created, and new galaxies and new stars show up in the middle of nowhere, and this happens again and again. So that's why there's a steady state occurring for the universe. And there was a lot of experimental evidence at the time that he wasn't that far off. What he ran into was these microwave tests where they were able to detect that there was initially a lot of microwave background radiation, which is what Penrose just talked about, and that fit a lot of the existing theories, and Hoyle couldn't match that, so his theory got disregarded. But Hoyle was the guy who came up with the term Big Bang because he thought the theory was ridiculous. He said, this is just taken straight out of the Bible, and there's no evidence for it. And this background radiation was taken as the evidence that there was something there that caused this. But here you can see that Penrose is saying that there still is a lot of difficulty in interpreting this sort of thing, that if there really was a bounce, then what's really going on here, because things aren't in equilibrium and gravity was ignored and on. And so this is something that people continue to work on, and we haven't seen the end of it yet. More than likely, the bounce will be the correct thing. But, that's because of what Ron observed, but we'll see. So let's look at the rest of
the initial condition. How does that work?
The point about...
Okay.
Isn't this close to what the Hindu model is?
The Indians view everything as cyclical. The Hindus, that there's cycle after cycle of the universe. We're just another cycle of the universe.
It seems to me it would make a lot of sense for them to explore these things.
No, it is. It's just that they're hard to explore because what sort of experiment do you run? How do you start up a new universe? you know, what, what
Well,
do I
but
do?
You could at least research the literature. You could at least.
Well, the people
You know.
have researched the literature at the wazoo. They've come up with theory upon theory, and there's a lot of evidence from what Penrose has done that it is cyclical. Okay, that his view his view of it being this conformal cyclability, that in fact when you think you're at the end of the universe, you're actually at the start of the new universe.
Well, it could be like those wave forms in the patterns. What's called that's created when the electron is when a wave is hitting.
The interference patterns.
Yeah, the interference.
Yeah. No, that's what they measure. They measure those.
It could be the edge of one is the
right. No,
the edge of the next one.
Yeah, no, there's several different telescopes that have been put in orbit that show, you know, this sort of stuff. I just didn't pull up any pictures from that because it takes us off into this cosmology. But
the entropy, you see, if gravity is the major contribution to the entropy, which it seems to be in the early universe, at least the absence of gravity, if you like, then you can say, well, what is the most likely situation if gravity were there? And you can make a good estimate of this because instead of thinking expanding universe, you think of a collapsing one. And then you think of it a little bit perturbed, and then you wonder what black holes will come and they form and they collapse and congeal. And then you use the Bekenstein-Hawking formula, and you work out what the entropy would arrive at in this completely messy general collapse. And you find that the entropy there has a figure, well, it's about 10 to the 124, which means that the improbability of it not being there is 10 to the 124. And so turning this around, you say, so how unlikely was the absence of gravity that we seem to see in the early universe if, you know, you imagine the creator sticking a pin in the base of all possible universes, you've got to find that little point, which is the proportion of that to the rest of it is something like 1 in 10 to the power 124.
Now, you don't believe that there was a creator with a pen, so how did that happen?
I've been puzzling over this for decades. But the idea of conformal cyclic cosmology does that automatically for you. And there are two features in this. One of them is that it snuffs off the gravitational degrees of freedom. There's a second point to this, which is when you think of eon after eon after eon, why isn't the entropy going up and up and up and up and up? It should, the second law says. Renormalize, if you like, the entropy value. It has now come down. There's never any violation of the second law. It's just I changed my mind about what I mean by entropy. And the new notion of entropy has gone way down. So it makes sense as far as I see. It remains to be.
Yeah, what he just said was, if the universe is continually expanding so that, okay, the entropy is increasing, but the entropy per unit volume is in fact going down because you have more volume. Okay, yeah, there's more entropy, but the volume grows faster than the entropy. That's what he just skipped over.
Wow.
The right answer.
Roger Penrose's grand vision is 3 worlds, 3 mysteries. The mathematical or Platonic world, the physical world, the mental world.
Okay, so let's get out of this. And we'll go back to see if we can go back to our PowerPoint. Go here. So there's links to, there's 3 longer talks here, you'll see. So then, for sake of completeness, I put in for Bruce and for everybody else too, we've got Buddhism, okay? So Buddhism has its own view of reality. I tried to summarize here some of the thoughts on this. So if you go into deep meditation, you realize that there is not a self and other things around you, that there is no duality. There's the loss of self-identity. And you cited this 3 nails. Do you want to talk about this, Bruce? the three nails?
No, you go ahead. I mean, that's one thing I'm not good at anymore is my memory doesn't work
Okay.
well. Yeah.
Okay, so the three nails are the nail of the view, the nail of meditation, and the nail of conduct. So we'll go through each of them. The nail of the view, okay, insight and clarity are off the charts. You're free of any doubt of what you're seeing. Everything is crystal clear, and right down to whatever level you could think of. It's inexpressible, and you have a perfect wisdom in what's going on once you achieve this non-duality. So that's the nail of the view. The second one is we have to do this in deep meditation. So as you continue and sustain this clarity, okay, it's not a one-shot thing, that all the negative emotions that you might have disappear without a trace, and a self-knowing awareness arises that you're part of how to say it, self-knowing. You're aware of everything, but there's no notion of anything negative. In fact, there's as we'll see, it takes you toward compassion, which is this nail of conduct. The fact is that you realize that you have compassion for others, you have compassion for yourself, and it's going to be impossible to do activities that aren't virtuous. That is the state that you end up in. And so the reality that we're talking about here is a different reality. I would, if I looked at what Penrose was talking about, it'd be a combination of the mathematical and the mental, in terms of what's going on, and the physical would just drop away. But that's my 2 cents. But this is a different view than what we just saw from these other views here. That the role of the observer in reality, and the idea of what we mean by reality with this double slit experiment. All of these things come into play. Buddhism addresses it by saying that really you lose all identity if you in fact look at true reality, and that's what really is going on here.
Well, it's the self that disappears, but what is actually there, like my sense of it is there's a vast comprehension of union. Everything, the universe is in union with itself, and the mind is part of that reality. It's just not separate at all. So love and compassion is not separate from everything else. And
the other thing that's implicit in this is that it was always there. This reality, was always there, or the world around you will evolve, but
well, it's sort of like what everyone's mind has a history over many lifetimes. Let's say, like thousands of lifetimes. And but what you think is real is only what's happened in this lifetime. So in the deeper part of your mind, there's this reality of understanding from the long history of the mind that's been going on forever. And it has a very different understanding of what is real. Because one of the biggest problems is the self. The self thinks certain things are real. This is where you're talking about the negative emotions, like anger, resentment, and so on. Everyone thinks they're part of the mind naturally, but when you actually have realization of non-duality, you found out that they never existed in the first place. It's sort of like that. It's just so different. It's kind of escapes any real understanding in an ordinary sense of the word. But where you encounter it is like when you encounter somebody who has it really highly evolved, like Namj Rinpoche did. Like his, that's when you can actually see it a bit better. But most people simply don't believe it. That's a possibility, simply because they don't even realize that they think a self is real when it doesn't actually exist. So it's kind of a quite a bit of difficulty in trying to explain it, especially myself, because I can't pull together the ideas that are behind everything.
No, it's okay. Yeah, that's fine. That's fine. I just want to get this out there as a different view of reality. I don't want to ignore it. So, because you had also Jesus of Nazareth, who apparently followed the same path, and said that really it's all within you, and if you actually learn to pray or meditate, that you'll see that that's what it is, and this will lead you toward love and compassion for yourself and for others. So it's not stressed enough, in my opinion, but it's what he said.
Right.
So anyway, so let's get out of this. And this is, I just thought a way to try and capture these disparate thoughts for tonight, to keep it, in some sense short and simple, but to show we still have trouble coming to grips with what is reality. And this is an attempt to try and touch on it in different ways, but at the end of the day, what is it? we can sense it. There's something out there that's reality, but we're not there yet.
Yeah. Eventually, maybe.
Yeah. If we work at it, we'll get there, but we're not there yet. So
another 10,000 years, right?
Yeah. Anyway, that's all I wanted to try and do tonight. We'll do something else for next week. So any more comments?
I guess I just don't really understand the purpose of the exercise.
Well, we've now gone through these different views of reality. So what is reality?
Knows.
Well,
yeah.
I mean,
here we have experiments.
Who's asking?
We have experiments that show that what we think of as reality changes in ways that we think shouldn't change.
Well, it's assuming that there's one answer. My question is, who's asking? From what point of view, that's going to determine the answer. As far as it can possibly go, it's going to depend on the paradigm of the asker.
Yeah.
You can't really do much better than that in the answering. And I think our perspective is just always going to be too limited to possibly comprehend.
No, I think we'll if we can evolve and learn to be to reach higher levels of consciousness, then we'll start to sense what the answer is. We're just down in the mud right now. I don't really see us making a lot of progress. We're we're sensing that there's something there, but you know, that's all we can say. So that's all I was trying to do. We'll see you next week. Have a good.
Okay.
Okay.